Hello, colleagues. My name is Michael Annor-Nyarko from Harbin Engineering University, China. My paper is titled Integrity Evaluation of a Reactor Pressure Vessel based on a sequential Abaqus-FRANC3D simulation method. My presentation will follow this outline: introduction, objectives, methodology, results, and conclusion. A key safety concern of nuclear power operators is to maintain the structural integrity of the reactor pressure vessel, which is critical and non-replaceable, and also technically determines the feasible lifetime of any reactor power plant. One of the main challenges aging vessels experience is the exposure to pressurized thermal shock, which arises due to temperature variations and internal pressures caused by the operational conditions of the reactor, be it severe or normal reactor operations. Now, a defect of a critical size in an aging reactor pressure vessel subjected to PTS, initiated by either an anticipated transient or a postulated accident, may rapidly grow in the vessel, leading to damage, leakages, or possibly failure of the vessel. Now, several potential PTS initiated by postulated accidents, such as the loss of coolant accident, have been investigated. However, one of the most frequent anticipated transients, which is inadvertent operation of the safety injection system, that equally induce significant PTS have rarely been studied. In this study, a sequential Abaqus-FRANC3D simulation method is developed for the evaluation of the integrity risks posed by inadvertent operation of a safety injection system on an aging reactor pressure vessel of a pressurized water reactor. Validation of the model developed will be based on comparing the output, which is the integrity parameter or the stress intensity factor obtained from our simulation method with the conventional extended finite element method. Our simulation method follows the flowchart in Fig 1 to evaluate the structural integrity of the reactor pressure vessel based on the selected PTS, which is the inadvertent operation. The 3D finite element model is built. Now, this model is used for the thermal-mechanical coupling analysis, which incorporates the mechanical loading and the thermal loadings from the selected PTS. Now, the thermal-mechanical analysis is performed to determine the highest thermal stress location in the 3D finite element model. A submodel is created from the highest stress location within the thermomechanical analysis. Now, this submodel captures the highest thermomechanical stress location obtained from the thermomechanical analysis. And this submodel also includes a postulated semi-elliptical crack, which is used for the next submodeling fracture mechanics analysis. Our simulation method is followed to determine the integrity parameter, which in this case is the stress intensity factor. Fig 2 shows the PTS induced by the inadvertent operation of the safety injection system. In Fig 2, you can see the pressure and the water temperature changes obtained by this anticipated operational occurrence within the nuclear power plant. Now, Fig 3 also shows the 3D finite element model used for the thermomechanical coupling analysis. And B also depicts the loadings and the boundary conditions applied for the thermomechanical coupling analysis. In Fig 4 shows the simulated results after the thermomechanical coupling analysis. In Fig 4, the section that has the highest stress location is around the nozzle area of the reactor pressure vessel. Now, Page 5 shows the submodel that was created after the thermomechanical analysis indicated the highest stress location. Now, the highest from Fig 5, the stress and the crack locations are shown in Fig 5. A crack, an axial semi-elliptical crack, is placed at the highest stress location, and the simulation is performed using our method. Now, Fig 6 shows the temperature distribution at the highest thermomechanical stress location. And you could see that the temperatures were within 250 to 230 degrees. And this temperature is considered to be high within the nuclear power operations. Fig 7 also shows the Hooke stresses obtained from the thermomechanical stress analysis. Fig 8 shows the axial stresses which were generated after the thermomechanical coupling analysis. And Fig 9 shows the integrity parameters calculated by our simulation method and the conventional finite element method. From the results obtained, both methods were in good agreement. However, the fracture toughness of the material of the vessel was, however, higher than the integrity parameter determined, which in this case is the stress intensity factor. Now, this indicates that an inadvertent operation of safety injection would have less impact on the structural integrity of the reactor pressure vessel. In conclusion, the applied sequential Abaqus-FRANC3D simulation method applied efficiently reduced the computational cost in evaluating the anticipated operational occurrence, PATS, induced stress intensity factors. Also, the stress intensity factors determined at the deepest crack tip based on our simulation method was in good agreement with the extended finite element method. This work serves as a foundation for our future study on the crack growth analysis and fatigue life prediction of an aging vessel subjected to an anticipated transient PTS loading. Thank you.